All right, we're going to talk about section 3.1, exponential and logistic functions. And we're going to start off by talking about basically the standard form of an exponential function is this right here, f of x equals a times b to the x. Make sure you remember that because of order of operations, we would do the exponent before we would multiply. So when you're looking at these, you can't ever multiply what a and b are together and then say that it's all to the x power. That doesn't work. You have to keep them separated if it's written like this. The b is the base of this exponential function. The a we call the initial value. We call it that because if you plug in a 0 where x is, then you get b to the 0, which is 1. And so at x equals 0, your first value is always going to end up being whatever a is. So it's called the initial value of this function. So an exponential function, the way we know that that's what it's classified as is that it has a number for its base. It could be a normal looking number like 2 or 3, or it can be a fraction, but it just has to have a number for its base and a variable in its exponent. And there can be other things in the exponent as well, but at the very least we have to have a variable in there. So let's look at this example. Are the following exponential functions? If so, state the initial value in the base. If not, explain why not. So we have y equals x to the 8th. And so we would look at that and say, no, that's not an exponential function. And it wants us to explain why. And so we would say that something about the base has a variable instead of a number, and the exponent has a number instead of having a variable. So on the second one, we have 3 to the x. Okay, and notice that this doesn't really have the whole a times b dx thing, but that's okay. This is still an exponential function because it's a number to an exponent that's got a variable. So we would say, yes, this is an exponential function, and it wants us to state the initial value. So the initial value, that's whenever I plug in a 0, what do I get? When I plug in 0 for x, what do I get? Well, 3 to the 0 is 1, so our initial value is 1. Or the other way of thinking of it is like this would be 1 times 3 to the x, telling us that our a in this case, which is our initial value, is 1. It also wants us to say what the base is. Our base is the number that's raised to the exponent, so that is 3. This last one, x to the square root of x, is a no. Again, we don't have a number for the base. I'm not actually sure if 2 to the square root of x, if we would still consider that an exponential function or not. I kind of feel like we would, but we're not going to probably see anything really like that. So that's how we tell whether or not it is an exponential function. Now let's do some computing. Compute the exact value of the function for the given x value without using a calculator. So this first one, they gave us f of x equals 2 times 4 to the x. So, and they want us to plug in a 0. So this is kind of to remind us about some of our exponent properties. Remember, 4 to the 0 is 1, so this is really 2 times 1, which is 2. So that's the answer on that one. Then we have f of x equals 4 times 2 to the x, so we're going to plug in -3. Remember that we don't like negative exponents, and the way we get rid of negative exponents is by moving them, if they're on top, down to the bottom of our fraction. So we would make this 4 over 2 to the +3. Because we moved it, we get to make it a positive. And then we would say, well, that's 4 over 2 cubed is 8. And then we can simplify that to 1/2. And last, we're plugging in 1/2 to -3 times 7 to the x. So that would be -3 times 7 to the 1/2. I think I meant to say x, and then it becomes 1/2. And so we really can't do anything to this except for maybe say, well, 7 to the 1/2 power, that's really the square root of 7. I mean, we could say that, and that would probably be our simplest answer. But we don't actually want the decimal. We want the exact value, and so -3 square roots of 7 would be our exact value. Next, determine the formulas for the exponential functions f and g whose values are given in the table below. So let's start off with f of x. The way we do this is we look at two things. First, we need the initial value, which remember is when x is 0, what are we at? We're at 5. That's the first thing we need. Then we need to figure out what the base is. And it just so happens that if we look at what we're multiplying by to get each of these numbers, to get from one number to the next, that's going to be our base. So sometimes with the fractions, it's hard to tell. So start here at like 5 to 10. What do you do to get from 5 to 10? You multiply by 2. What do you get from 10 to 20? You multiply by 2. And if you work backwards, hopefully you can see, okay, well, if I had 5 halves and I times it by 2, yeah, that would give me 5 because the 2's would cancel out. And same as up here, we would get 2 times 2. So that means my base is 2, and it's going to be to the x power. Let's do g of x. Okay, so I look at when x is 0, what is my function? It's 9. So 9 is my initial value, so it goes where a is. And then I would say, okay, what do I multiply by in each of these cases to get the next number? Well, in each case, my number's getting smaller, so it's going to be like I'm dividing by something. To get from 81 to 27, we divide by 3, which is the same thing as multiplying by 1/3. And if we look, each one of these, that's the case that we are multiplying by 1/3. So we would put 1/3, and we'd probably put it in parentheses and say that's to the x power. Now, we have the application, basically, of exponential functions is looking at either growth models or decay models. So this green box down here is talking about if we have an exponential function, f of x equals a times b to the x, and if a has to be positive for this to be the case, otherwise it flips your graph around and makes it a little different. As long as a is positive, if b is greater than 1, that means the function f is increasing and is an exponential growth function with the base b as its growth factor. And if b is less than 1, the function f is decreasing and is an exponential decay function with the base b as its decay factor. So let's look at the two examples up here we did. For f of x, we would call this exponential growth because our b, which is 2, is greater than 1. And our growth factor is 2, because that's what b is. On the second one, we would say that this is exponential decay because our b is a number that is less than 1. It's a fraction that's less than 1. And so it's exponential decay. Our decay factor is 1/3. Let's talk about the standard graph of exponential functions. And so we're really talking about, like, if I have f of x equals b to the x, where I have something bigger than 1, what does that graph look like? And then we're going to look at, well, if b is less than 1, what does that look like? And we're going to look at all of the normal analyzing things that we do with graphs. So for b to the x, if I don't have an a in front, that's really like there's a 1 in front. Our initial value on this problem is going to be 1. So I would put a tick mark and I would put a point at 1. The next value whenever I plug in 1, if I plug in 1 here, b to the first power is b. So we don't necessarily have to know what that b is, but somewhere there's going to be a b, and that's where we are at 1. And so if b is whatever this number is, then that's where it is. When we go to the left on this graph, we get closer and closer and closer to the x-axis without ever getting there. And then as we head toward the point that we have drawn, that's b, we just keep continuing to go up and up and up. And so that's our graph. So let's talk about the domain. My domain, the x values I'm allowed to get, I can get any of the x values that I want to. Okay, but for the range, the way these work is it's kind of like I have an asymptote for the x-axis. I'm never actually going to get to 0. I'm just going to get closer and closer to 0. And then my graph will increase until it gets to infinity, or it'll go toward infinity. Is it continuous? Yes, I can draw it without picking up my pencil. Is it symmetric? No, it's not symmetric on either axis or about the origin. Is it bounded? Remember, bounded means is it like something stopping my graph from going either to negative infinity or positive infinity? And there is. And in fact, we would say that it's bounded below, because it's like saying, hey, there's like this imaginary line here below my graph that graph is never going to cross. Extrema, on all of these, we're going to say no extrema. Asymptotes, I do have an asymptote. It's at the line y equals 0. And as long as we haven't shifted our graph up or down, that's always going to be the case that we have an asymptote at 0. The end behavior, we use limits to describe. So we say the limit from x to negative infinity of our function, so we could call that f of x. Well, as I get closer and closer to negative infinity for x, I'm going to get closer and closer to 0. Then as I approach positive infinity in f of x, I'm going to get closer and closer to positive infinity because we're increasing to the right. Now, if my function has a fraction for b, something that's less than 1, okay, I still end up having this tick mark at 1, my first point at 1. But then whenever I try to plug in 1 over here, I'm going to have a fraction to the first power. So this direction, it's going to be getting closer and closer to the x-axis. The other direction, if I plug in -1, that flips my fraction. And so that's where I'm going to end up being able to put my point at whatever b is and drawing the graph this way. So it's really going to be similar on these properties. A couple of them might be different. The domain is still negative infinity to infinity. We still are going from 0 to infinity for our range. We are continuous. There's no symmetry. We're still bounded below. Still no extrema. Our asymptote is at y equals 0. And then our end behavior will be flipped. As we approach negative infinity, we're going to be rising, and so we're going to get closer and closer to positive infinity. As we head toward positive infinity for our x, we're going to get closer and closer to 0. So the main things that could change on this would be if we flip it across the x-axis, we could end up with it being bounded above instead of below. If we shift up or down, that'll change our asymptotes, but most of them are going to be pretty similar to this. So I'm going to stop the video now and do part 2.